Hello everyone, welcome to our CVPR 2022 tutorial on performance measures in visual detection and their optimization. We are three researchers from the Department of Computer Engineering, Middle East Technical University. My name is Emre Akbaş and I will be giving the first part of the tutorial. My colleagues Sinan Kalkan and Kemal Öksüz will be delivering the second and third parts of the tutorial. Before starting the first part, let's take a brief overview. Our tutorial is intended for researchers and practitioners who are working on visual detection problems. By visual detection, we particularly mean the following four problems: object detection, instance segmentation, key point detection, and panoptic segmentation. This tutorial is especially for you if you are particularly interested in the evaluation of visual detectors or curious about the limitations of commonly used performance measures, or if you have been thinking about how we can unify the training and evaluation of visual detectors, this tutorial is intended for you. Our tutorial consists of three main parts. The first part will give us the background and basics on evaluating visual detectors. We will introduce the visual detection problems and describe the widely used performance measures as well as the recent advances in this subject. In this part, we will basically be explaining average precision, the most widely used performance measure, and briefly talk about its limitations. Then we will introduce the panoptic quality and the localization precision recall error metric. Finally, we will close by introducing more recent progress in the field, namely AP variants such as AP fixed and AP pool, probabilistic detection quality, boundary intersection over union, and optimal correction cost. In the second part, we will present an analysis of the performance measures that we introduced in the first part. We base this analysis on three desirable properties to find in a performance measure, which are completeness, interpretability, and practicality. We will have a closer look on average precision, panoptic quality, and localization recall precision error. We will present analysis of these measures in terms of completeness, interpretability, and practicality. In the final part, we will talk about the optimization of performance measures. We will draw your attention to an often overlooked fact, which is the discrepancy between the training objective and evaluation measure in visual detection. A typical example of this discrepancy would be an object detector which uses some sort of cross entropy loss and L1 loss as training objectives, but its performance is evaluated by average precision. These objectives are obviously not the same. We are going to talk about recent efforts that try to close this gap, all of which are based on ranking-based loss functions. So we will introduce these ranking-based loss functions, which are actually not differentiable, but we will introduce a method called the identity update, which gives us a gradient to minimize these non-differentiable ranking-based loss functions. We will give three examples of such loss functions. These are average precision loss, ALRP loss, and finally rank and sort losses. We hope that you find our tutorial useful. Okay, after this overview, let's start the first part of the tutorial, the basics of evaluating visual detectors. Let us look at a more detailed table of contents for this part. We will start by introducing visual detection tasks and talk about how the performance is evaluated in these tasks and why it is important. Commonly used performance measures will follow. We will describe how average precision is computed and briefly talk about its limitations. An in-depth analysis of AP will be given in the second part of the tutorial. After AP, we will present panoptic quality and localization recall precision. Finally, more recent advancements in this subject will follow. These are the AP variants, namely AP fixed and AP pool. Then we will go over probabilistic detection quality, boundary intersection over union, and optimal correction cost. So let us first define what visual detection is. We start with an input image and feed this to a visual detector, which is typically a deep neural network. There might be some pre-processing and post-processing steps here, but they are not shown for simplicity. The visual detector outputs a list of detections or predictions. The size of this list, N here, is arbitrary, and it depends on the content of the image and the configuration of the visual detector. Each detection in this list is associated with three elements: an object category, a confidence score, and a spatial support. The category is obviously a categorical variable which identifies the predicted class for this detection. Confidence score expresses the confidence of the prediction. It is typically a number between 0 and 1. Lastly, the spatial support describes the geometry of the region that is associated with this particular detection. The spatial support can be as simple as a rectangular box, or it can be an arbitrary shaped region. An example visual detection task is object detection. A typical output for this task would look like the detections shown here. There are two detections shown. Each has a category, which is zebra in this case, a confidence score, and a bounding box denoting the spatial support of the detected object. There are four visual detection tasks that conform to the definition we just gave: object detection, instance segmentation, key point detection, and panoptic segmentation. Object detection is the task of recognizing and locating instances of objects using bounding boxes. In key point detection, the goal is to detect important points of an object instance that characterize the pose of this object. Instance segmentation is similar to object detection in the sense that it detects individual instances of objects, but the difference is in the type of spatial support. Instance segmentation uses a dense pixel-wise labeling, and objects are marked with arbitrary shaped regions. And finally, panoptic segmentation combines instance segmentation and semantic segmentation. Individual object instances are segmented and given separate IDs, and in addition, background classes such as road, sky, building, trees, etc. are segmented. These four tasks mainly differ in the type of spatial support they use, but they can also differ in the type of confidence scores. While object detection, instance segmentation, and key point detection tasks associate a floating point confidence score with each detection, the panoptic segmentation task uses a confidence score of 1 for all of its detections. We call such detections as hard predictions. So it is desirable for a visual detection performance measure to handle all these different cases. Okay, let's now talk about what evaluation is. Remember our visual detector from a few slides back. This visual detector takes in an input image and predicts a set of detections. To evaluate these detections or to measure their quality, we need ground truth detections or annotations. These can be created by a human annotator. The list of ground truth items is again a list of arbitrary size, which depends on the content of the image. Each ground truth item G is associated with an object category and a spatial support. In ground truth items, confidence score is usually not recorded. It is automatically assumed to be 1. Now the question is, what is the amount of overlap between D and G, or how similar is D to G? This is obviously not a trivial problem, since we are essentially comparing two lists with different sizes, and the elements in each of these lists are not simple entities. They have categories, confidence scores, and spatial supports. So any evaluation or performance measure that compare lists D and G needs to compare an individual detection, for example D2, with an individual ground truth item, for example, GM. And this comparison needs to account for two things: to measure the overlap between their categories, in doing so taking into account the confidence scores, and to measure the overlap between the two spatial supports. Measuring the overlap between two categorical variables is fairly straightforward. So let's look at how we can measure the overlap between two spatial supports. We will use intersection over union for this. Suppose we are comparing an individual detection DI with an individual ground truth annotation GJ. To measure the overlap between their spatial supports, in this specific example, bounding boxes, we compute the area of their intersection and divide it by the area of their union. When the two boxes are identical, we have a perfect intersection over union score of 1, and when the two boxes do not overlap at all, that is, they do not intersect, then intersection over union becomes 0. After this brief digression on localization quality, let us go back to the topic of evaluation. Evaluation in visual detection is important because it is one of the most important factors that drive progress in our field. And in some problems, maybe it is the only factor that is driving progress. Because of this, there are some desirable properties that evaluation or performance measures must have. First, evaluation must be complete. That is, given the list of detections and the list of ground truth, the evaluation should properly reflect all important aspects of performance. In the case of visual detection, these aspects are recall, precision, and localization. The evaluation measure must be interpretable. The higher its interpretability, the more insights it would give us about potential ways to improve visual detection. And finally, it should be practical. Any issue that arises during practical use of a performance measure diminishes its practicality. For example, any discrepancy between the well-defined theoretical description of the evaluation measure and its actual application in practice, or any shortcoming that limits the applicability of measure to certain cases. Now it is time to go over performance measures one by one. We will start with average precision, or AP for short, because this is the de facto performance measure or the most widely used performance measure in visual detection. Suppose we are given a set of detections and a set of ground truth annotations on a number of images. Here we will illustrate the computation of AP over just a single image, just for simplicity. To compute AP, we need to compute the recall precision curve, as AP is the area under the recall precision curve. And to obtain a single point in the recall precision curve, we actually need two thresholds, one for the detection confidence scores and the other for the intersection over union values. Let these thresholds be, for example, 0.3 and 0.5. Given these, the first step is to eliminate detections with confidence scores lower than t is equal to 0.3. On this particular example, there is one detection with score lower than 0.3. This detection has a score 0.1, so according to this threshold, it needs to be eliminated. So we eliminate it. The next step is to match the remaining detections with ground truth boxes based on localization quality, that is, the intersection over union. We check all possible pairs of detections and ground truths, and if a detection matches with a particular ground truth box with more than the given intersection over union threshold, which is 0.5 in this case, then we declare a match. Here, in this example, we have two matches. This particular detection matches with this particular ground truth item, and this detection matches with this ground truth item because they both have intersection over union values larger than 0.5. Note that after the matching is complete, there is one ground truth box which did not match with any detection, this one, and a detection that did not match with any ground truth items. Next step is to count the number of true positives. Because there are two matches, as shown here, the number of true positives is 2. We can also count the false positives, which is 1, which comes from this detection which did not match with any ground truth. And we can also count the false negatives, which is also 1, and it comes from this ground truth detection which did not match with any detections. We can also relate these numbers to the total number of ground truth boxes and total number of detections. The total number of ground truth items equals number of true positives plus number of false negatives, and the total number of detections equals number of true positives plus number of false positives. From here, we can now compute recall and precision. Recall equals number of true positives divided by the total number of ground truth annotations. In this case, it turns out to be 2/3. And precision, which equals the number of true positives divided by the total number of detections, is also 2/3. These two numbers together gives us a single data point in the recall precision curve, as shown here. We just obtained a single data point in this curve. Now, if we do a systematic sweep of the threshold value for t and repeat these 3 steps we just described, we will obtain more points in the recall precision curve, and then our plot would be complete. Finally, theoretically speaking, we would obtain a plot that looks like this, and the area under this curve is what we call average precision, or AP. However, what happens in practice is that you get a non-monotonic curve, because when you, for example, decrease the threshold t a little bit, the recall might stay the same, but precision might decrease. That is why you get these vertical drops and the zigzag behavior. To tackle this, the curve is smoothed out to keep the max precision value to the right at any point. This is called precision interpolation, and this red curve is the result of that interpolation. In the 2 most widely used data sets in object detection, which are Pascal VOC and MS-COCO, this smoothing is being automatically done for you in the dataset's official evaluation code. Finally, the last step is to compute the area under this curve. In Pascal VOC, area under the curve is approximated by summing the curve over 11 regularly spaced points in the recall axis. And COCO does the same thing, but it uses 101 points. The Pascal dataset uses only one intersection over union threshold, which is 0.5, and hence the name AP50. But the COCO dataset uses 10 different intersection over union thresholds in this range from 0.5 to 0.95, and this produces 10 different AP values, and these are averaged together to get a final AP value. Lastly, note that we plotted this curve for just a single object category. In our example, it was the zebra category. Usually in visual detection datasets, there are many object categories, and to report an overall performance on the dataset, AP values over classes are averaged. This is called MAP in Pascal VOC and just AP in COCO. There are well-known limitations of AP, and we are going to talk about these in depth in the second part of the tutorial. Here we will briefly mention 2 of them. First, localization quality is only loosely taken into account in AP, so it is actually not properly accounted for. For example, given this particular object and its ground truth annotation, let us consider these three detections. This one seems to perfectly overlap with the ground truth box, and this one seems to cover only the top half of the ground truth item, and this one covers the lower half. But all of these three detections have intersection over union scores that are larger than 0.5. And because of this fact, they are equally good for AP50. And this is a limitation for AP. It does not properly factor in the localization quality. Another major limitation of AP is that it lacks interpretability. The AP score itself does not provide any insight in terms of the important performance aspects, namely false positive rate, false negative rate, and localization error. Here we see outputs of three different object detectors on the same input image. The blue color boxes denote ground truth, white colors denote true positives, and orange ones are false positives. These three detectors have different strengths and weaknesses. For example, in the first one, let me open the laser pointer. In the first one, there are two true positives with very high intersection over unions, but two other objects are missed, this one and that one. In the second detector, all four objects are successfully detected, but some of them with low confidence scores. And also, there are many false positives, these orange boxes. In the last detector, detector 3, again, four objects are detected. There are four true positives, but this time with even lower scores overall, and there are now fewer false positives. Obviously, these three detectors have three different cases. Yet, these three different results with very different characteristics yield the same AP score. As you can see here, AP 0.5, 0.5, 0.5. We will talk about this and other limitations of AP in the second part of the tutorial, but this example just shows that AP lacks interpretability. Now let's move on to our next performance measure, which is the Localization Recall Precision Error Metric, or LRP for short. LRP was proposed in ECCB 2018, and it was extended with more analysis, applications, and extensions in the Pattern Analysis and Machine Intelligence Journal in 2021. Let us walk over how LRP is computed by revisiting the same object detection example that we used for explaining average precision. As in the case of AP, we need two thresholds, one for the confidence score and the other for the intersection over union. Let's pick the same threshold values as we did before, 0.3 and 0.5. Given the 0.3 score threshold, detections with lower scores should be eliminated first. This is the first step of the computation. Then we match detections to ground truth boxes based on their pairwise intersection over union values. And as a result, we have two true positives, one false positive, and one false negative. And this one was already eliminated. So these are our numbers. Okay. LRP between a set of detections and a set of ground truth boxes is computed as a ratio of total matching error and the total sources of error. So LRP's maximum value can be 1 and its minimum value can be 0. Let us first look at the total matching error. This expression represents the total matching error. In this expression, we take into account all types of errors. False negatives, that is the misses, false positives, and the localization errors of true positives. Each true positive in the detection contributes to the LRP error proportional to its localization error, which is 1 minus the localization quality of that particular detection. One obvious choice for this LQ function is the intersection over union, and this is divided by 1 minus tau, where tau is the intersection over union threshold. This division ensures that for each true positive we have a localization error between 0 and 1. Each false positive contributes to LRP by 1, and similarly each false negative contributes to the LRP error by 1. The sum of all matching errors is divided by Z, which is the sum of all total possible error or total sources of error, which is the summation of false negatives, false positives, and true positives. Now let's consider some extreme cases of this expression, this LRP, to better understand how it works. Suppose all detections matched ground truth boxes, so that we have 0 false negatives and 0 false positives. In this case, the only error to contribute to LRP would be the localization errors, this term. Note that in the case of AP, because any localization above the intersection over union threshold is good enough, recall and precision values would not change. Now, suppose all detections were false positives. Then we don't have any true positives or any false negatives. And in that case, LRP would simply be number of false positives divided by number of false positives, which is 1, and that is the maximum possible value for LRP that LRP can take. LRP can be written in a different way. It can be expressed explicitly in terms of its localization, recall, and precision components. LRP localization component gives us the average localization error computed over all true positives. Recall error is basically 1 minus recall, which equals 1 minus number of true positives over divided by the number of ground truth items. And then the precision error is 1 minus precision, which equals 1 minus the number of true positives divided by the number of detections. In this way, through its components, we can explicitly obtain performances regarding different aspects of a visual detector. For example, you can compare two different object detectors by just looking at their values over these components and tell that which detector is weak or strong in terms of which aspect, and so on. So far, we have seen the computation of LRP for just one specific confidence threshold T. A systematic sweep of confidence threshold T yields this curve. It's called the SLRP curve. On the x-axis, we have the confidence score thresholds, and on the y-axis, we have the LRP values. We call the minima in this curve as optimal LRP, or OLRP for short. It represents minimal achievable LRP error, and this point represents the overall performance of a visual detector. As with LRP, OLRP is also interpretable, and it can be separated into its three components. These three values, without the need for looking at any curves or plots, would give us insights about the strengths and weaknesses of the visual detector. We do not need to compute separate LRP or OLRP values for different intersection over union thresholds. We will talk more on the analysis of LRP and how it addresses all the limitations of AP in part 2. And in part 3, we will talk on how LRP can be used as a training objective so that the training and evaluation of visual detectors is unified for improved performance. So far, we explained LRP over an object detection example. But can it be applied to other visual detection tasks? The answer is yes. All you need to do is to define an appropriate localization quality function for the task. So let's take key point detection as an example. An appropriate localization quality for this task is what is called the object key point similarity function, OKS for short. It basically computes the distances between the ground truth point and the predicted point. Then negative of this is passed through an exponential function. Finally, you plug this in the LRP formula. This OKS gets is substituted here for LQ. And the rest is just the same with the object detection case that we described in the previous slides. We do a systematic sweep of the confidence threshold T and obtain an LRP curve, the minimum of which gives us OLRP, or the optimal LRP point. For more applications and extensions of LRP, you can visit our paper. Alright, now let's look at another performance measure called the Panoptic Quality, and Panoptic Quality was proposed in CVPR 2019. Unlike AP and similar to LRP, PQ, or Panoptic Quality, properly takes into account recall, precision, and localization. Here is its formula. It is similar to that of LRP in structure, but unlike LRP, which is an error metric, PQ is the higher the better measure, similar to AP. So let's look at this expression for Panoptic Quality. As the localization quality, which is intersection over union here, denoted by IOU, as the localization quality increases, or the intersection over union quality increases, the PQ will increase. And as the number of errors, like number of false positives and number of false negatives, then PQ will decrease accordingly. PQ can be written as a product of two quality measures: segmentation quality and recognition quality. Segmentation quality represents the average intersection over union of the true positives, and recognition quality represents the classification performance in the form of an F measure. Overall, Panoptic Quality is interpretable in the sense that segmentation and recognition qualities are separately computed and can be reported. However, its interpretability is limited since recall and precision are not explicitly given. And finally, Panoptic Quality is limited to hard predictions. These are those predictions without confidence scores. Theoretically, PQ can be extended to evaluate soft predictions, but this extension was not provided in the original paper. We will talk more about PQ and its analysis in terms of desirable properties of a performance measure in part 2. After covering AP, LRP, and PQ, now we will go over more recently proposed performance measures. The first measure we are going to look at is the recently proposed AP variants, which are AP fixed and AP pool. In this paper, the authors showed that AP, as it is implemented in the common benchmarks, for example COCO, is actually gameable. They discover an unintuitive re-ranking strategy that can increase AP substantially, in this example from 25.5 to 27.2. By reducing the number of detection outputs for frequent classes, person in this case, and increasing the number of rarer classes, bicycle in this case. This re-ranking balances AP better across categories, but counterintuitively removes some higher confidence true positives, while also adding some lower confidence false positives, as shown in this figure. The root cause for this phenomena is that the standard AP implementations limit the number of detections per image. For example, in COCO, it is limited to 100 per image. And this creates problems. Rare classes are disfavored, and because they usually have lower confidence scores. Cross-category confidence calibration is ignored, and AP for a single class is not really independent from other classes. To fix these issues, the authors propose AP fixed. Instead of limiting the number of detections per image, they limited per class over the entire dataset. This ensures class-independent evaluation, so AP is not gameable anymore. However, the cross-category score calibration is ignored. As a better evaluation measure that takes into account cross-category calibration, they propose AP pool. As we said in the previous slide, standard AP and AP fixed compute AP per class and then take average. This ignores cross-category score calibration. To reliably take this into account, AP pool pools detections from all images of all classes, and a single recall precision curve is computed. And this rewards properly calibrated detectors. The next performance measure to visit is the probabilistic detection quality proposed in WACV 2020. This paper actually proposes a new task. It is the probabilistic object detection, where uncertainties regarding both the semantic label and the spatial support are taken into account. For example, on the spatial aspect, instead of directly outputting bounding box coordinates, the probabilistic object detector outputs distributions for the top left and bottom right corners for an object. And these two distributions together define a spatial probability distribution as shown in this figure. PDQ can evaluate such probabilistic outputs, but it can also evaluate conventional object detection outputs with box coordinates. In PDQ, for all possible detection and ground truth pairs, PPDQ is computed. This consists of a spatial quality term times a label quality term. Based on these PPDQ values, a Hungarian matching algorithm is used to establish which detection matches with which ground truth. Then, overall PDQ is computed using this formula, which is structurally very similar to PQ and LRP as well. Here, this Q function is actually PPDQ, which measures the spatial quality and label quality for a detection ground truth pair, matched pair. And then this total quality is divided by the number of true positives, number of false negatives, and number of false positives. Spatial quality can take into account the mask of the object. This is an additional feature of the performance measure. And PDQ can evaluate probabilistic spatial outputs. The next performance measure is boundary intersection over union. This is a measure that is specifically proposed for segmentation tasks. And here is a motivational figure from the paper. Here we see 3 segmentation results, as shown here, for an object whose ground truth segmentation is given on the top left. The usual quality measure used in this task is mask intersection over union. And although this measure ranks these detections correctly, it is not very sensitive to the qualities of the boundary, as you can see from the differences between these 3 results. The new boundary intersection over union, however, is very sensitive to the boundary quality, and it intuitively better measures the segmentation quality as demonstrated by these numbers. Given ground truth mask G, and the prediction mask P, boundary intersection over union first computes the set of the original mask's pixels that are within distance d from each contour, and then computes the intersection over union of these 2 sets. So you basically compute these blue region and orange region, which are within distance d from each contour, and then we apply intersection over union on these blue and orange regions. The last performance measure we present in this tutorial is the optimal correction cost, which is from this CVPR actually. Authors in this paper start by illustrating deficiencies of AP very well. This example from the paper shows the output of 3 detectors on 3 different images. So each row is a different detector and each column is a different input image. In terms of AP, this column, the best detector is the third one, this one, because it performs perfectly for the donkey class and it achieves a perfect score of 1, but it misses all instances of ducks and it achieves a AP score of 0. And when you average AP scores over classes, you get 0.5. On the other hand, detector A and detector B achieve equal AP scores, 0.28, although their correct detections are not distributed homogeneously. The first one gets 2 correct detections in the first image and 1 correct detection in the second image, but the detector B gets all the detections correctly in the first one, but none in the second one. So this example basically illustrates the biases of AP over images and over classes as well. As a fix, the authors propose the optimal correction cost. So given a set of detections here and the ground truth items, they first construct a cost matrix. Each element in this matrix represents the cost of correcting that pair of a detection and the ground truth. And correction includes correcting its label plus its localization quality. After this cost matrix is constructed, optimal assignment of the detections to the ground truths are determined by solving an optimal transportation problem. And this gives us this labeling which denotes the optimal assignments. And based on the assignments, they aggregate the correction costs as the measure of final detection performance. And here we complete the first part of the tutorial. In the next part, we will talk about desirable properties of a performance measure and will present a detailed analysis of AP, LRP, and PQ in terms of these properties.